All right, everyone. Here's our makeup SI since the buildings were closed. So for naming alcohols, we didn't go over this in class. However, it will be on the exam, of course, and on the final, so we will go ahead and name these. For alcohols are a high priority functional group. So more than anything we've ever seen before, alcohols are going to take priority in terms of nomenclature. I'm always going to number the chain such that the alcohol is at the lowest numbered carbon. I have to assign stereochemistry to these, so this alkene is going to be E since it's trans. For here, we can say oxygen is going to be number 1 since it's got the highest atomic number. Here, it's got phantom atoms. The alkene takes higher priority over the methyl group coming off. So this is an R stereocenter. So I'm just going to name it as R. So the way that we name this is it's going to be hex, and then to specify the position of the alkene, I'm going to put 3-ene, and then 2-ol. So it's a little weird to name it like that, but that's just how we do it. Hex 3-ene, 2-ol, and then I specify stereochemistry 2R, 3E at the beginning to go ahead and specify what those stereocenters are. Same thing over here, so I'm going to have to, so for cyclic systems, because the alcohol is the highest priority, I'm going to always number it such that the alcohol is number 1. The alkene is number 2, since that has a higher priority as well, so I do want to go in the kind of counterclockwise direction here. We also have a 3-methyl group coming off, but we need to assign stereochemistry of this alcohol first. So 1, here's 2 over here. The alkene takes priority over the alkane because of phantom atoms. This appears like it's going to be S, but really we have to flip it and make it R, so it's an R stereocenter. We flipped it because the hydroxy group is coming back. So this is R. Essentially what I'm going to put here is I'm going to put R. Since I have a 3-methyl group, so R 3-methyl, and then hex, so cyclohex. The alkene is at the 2 position, 2-ene. And then I actually don't have to specify the position of the alcohol since because it's the highest priority functional group, I already know that I'm going to name the ring such that the alcohol will be at the lowest number. So I actually don't have to specify that it's at the 1 position because it's implied based on the name. But you can put ene 1-ol and that's still fine. It's just not, I guess not IUPAC. IUPAC would be displeased with you if you did that. But yeah, you should know that enol is fine at the end. I don't have to specify the stereochemistry of the alkene since it's in a ring. So that's a sufficient name there. 2 reasons why this reaction will not work, right? So we learned in class, hydroxy is so the hydroxy right here. The reason why this won't work is that this alkyne will simply just deprotonate the alcohol to give this. So, and also the protonated version of the alkyne. So, reason number 1 is a acid-base reaction will happen. So acid-base is favored. Another thing is, right, SN2 is harder to do than acid-base. So acid-base is relatively fast. So acid-base is fast. It's one of the fastest reactions we learn in the class. It's just this general deprotonation step. So not only, so the acid-base reaction happens, and that's because the SN2 is harder to do than the acid-base reaction in terms of kinetics. So that the acid-base happens at a faster rate. Replacing OH with the tosylate group, so this is a tosylate, that makes it a better leaving group. Why does that do that? So ordinarily, let's just show this leaving. Ordinarily, in this case, right, primary carbocation, not great. The point here is like, let's just compare the leaving groups. So tosylates take a long time to draw. I'm not even going to show the carbocation since it's not important here. What's important is let's compare hydroxy versus the tosylate group. So OH, the only thing going for it is electronegativity. So OH, it's electronegative. Yeah, oxygen's electronegative, so it's kind of happy with that negative charge, but it's really not that happy. Compared to the tosylate, this has, get ready for it, resonance. It's got resonance out the wazoo. You see we have this benzene ring here. We have these SO double bonds that can contribute in resonance if we wanted to draw the arrows like that. I'm not going to show that. But yeah, we could draw those resonance arrows. So it is resonance. It also has induction because the oxygen atoms nearby are also electronegative. So that's going to induce a partial positive on the sulfur. That's going to stabilize through induction. So that's generally going to be better. And oxygen is still electronegative. So all of these mean tosylate is a better leaving group. So it's just more stable. The main thing here is going to be resonance. It's just so many resonance structures that can be done there with the S to O double bonds there. All right. Number 4, we want to show a mechanism for the addition of the tosylate group. So a tosylate group looks like this. You'd be given this on an exam. It looks like this. As we discussed previously, it looks like that. The way that this reaction would work for the purposes of chapter 13, we'll just say it performs kind of like an SN2 reaction, so like that. Without overcomplicating any of the steps, it'll just do that. So it'll just add through conjugate addition, like that. And then Cl minus will just steal that proton away. To form the final tosylate product. So that's that mechanism there. So the following reaction below did not work. What is the real product? So why might this not work? Let's draw a mechanism to figure out why. So we have our little alcohol here. It can add, through the same mechanism, it can add to the tosylate. So we literally just went over this. So I'm just going to shorthand it and just say, yeah, it's going to form the tosylate. The question is, so I'll draw out the full thing, in fact. So, in fact, right, this would happen right here. However, you see in our reaction, up here we formed, so Cl, that's actually a really poorly drawn Cl. This Cl is going to take away the hydrogen. So that's going to make HCl, and it's the same thing in this reaction. So really, we're making HCl as an intermediate, and we know from chapter 8, alkenes immediately react with HCl to form a carbocation. And that means that this right here is the real product that we're going to actually get. The way that we fix this, right, so is shown in number 6. So tosylates, here we are, so if I went ahead and did the addition step here, that's not what I wanted to do. So I went ahead and did the addition here with the tosylate. I would get my alcohol protonated still, right here, with the tosylate group coming off. Another thing that would happen, though, is that now I have triethylamine right here. That's a base that can go ahead and take away that proton. So essentially what that means is this will no longer actually be able to react with the alkene since there's no actual HCl formed. It's getting a little rough over here on the room. There we go. So that's a tosylate here. Added. Now the triethylamine has the proton instead of HCl. So now HCl cannot react to that alkene. So I've gone ahead and made this down here. I've gone ahead and made, this is completely separate from question number 7. I'm just running out of room. We go ahead and have that tosylate functional group. That's a good leaving group. So cyanide, through an SN2 reaction, can go ahead and take off the tosylate. And then during SN2, the functional group adds to the opposite side. So this will be on a dash. So the final product here is going to be the same thing, except that now cyanide is on a dash, like that. Go ahead and erase this to get some more room. Predict the product for the following reactions. SOCl2, SOCl2. This will react basically to replace an alcohol group with a chloride. It'll do the same thing here. This is a meso compound, so there's no stereochemistry. This is a chiral, no stereochemistry. So that's it. I'll go ahead and show the mechanism since it's fun to do, I guess. That is not SOCl2. This is SOCl2. So I'm just gonna say it happens like this. So we just kind of sub in this sulfur group for the chloride, and then we get a chloride that's minus. What you'll notice here is that this is a good leaving group. So that can go ahead and do an SN2 reaction. So that can go ahead and do that. Like that to form our product. So that's the mechanism for that step. So that's the worksheet. There you go.